Hello, my name is Huda Kirala, and today I will be talking about how Simulated Multiple Reference Training, or SMART, improves low-resource machine translation. I'm a final year PhD student advised by Philip Kuhn at Johns Hopkins University. This is joint work with him, as well as Brian Thompson and Matt Post. I'm also on the job market this year, so please reach out if you're hiring. In this work, we will be using target-side paraphrasing to overcome data sparsity in low-resource settings. And we're going to do this by integrating a paraphraser directly into the loss function of the neural machine translation model. And what's cool is that we can leverage a strong paraphraser as long as the target language is sufficiently high resource. So let's take a look at a motivating example. There's so many ways to translate just this one short sentence. For example, instead of saying the turtle beat the hare, we could say that the turtle won against the hare. And by training on just one translation, we're missing out on additional data. In high resource settings, our models are likely exposed to similar sentences and different translations of them, but in low resource settings, we just don't have enough data and can't afford to miss out on additional translations. In this work, we will be using a paraphraser in the training objective to simulate training on the full space of possible translations. But before we get into how to integrate this into the loss function of the neural machine translation model, I'm going to quickly recap a standard NMT model, and then I will talk about what we will change. So here I have a cartoon of neural machine translation inference. And I'll be abstracting away a lot and just highlighting what will be relevant in this talk. So the model will take as input a sentence, and in this example, that'll be a Spanish sentence. And then we will get a probability distribution over the size of the target vocabulary as we're translating into English. From there, we can select the highest probability token, and we'll feed that back into the model and condition on it as we generate subsequent word predictions. These models are trained end-to-end on parallel text, and the loss comes from one word prediction at a time. These models are very data hungry. Ideally, they'd be trained on millions of parallel sentences. Here we have our example parallel sentence, and we'll convert that into one-hot vectors for training. The standard way we train these models is that for every token we produce in training, we will compute the loss to backpropagate. We're going to take the output distribution of the neural machine translation model we're training, and I show that in purple, and compute the cross entropy with the gold standard reference distribution. In this case, the reference is a single word, so for the gold target, we have a one-hot vector. But in general, we can compute the cross entropy between any two distributions. And again, there are so many different ways to translate even this simple sentence. And by training on just this one, we're missing out on additional data. You can think of these different translations as paraphrases of the English target sentence. So we are going to integrate a paraphraser in the loss function of the NMT model to simulate training on all the translations. Under the hood, the paraphraser is a lot like the MT model we looked at. We will get a distribution for each output token, and we're going to use that distribution in the cross entropy loss of our MT model. When decoding, at each time step, we could take the highest probability token, and I show that path we'll end up with in black in the tree of paraphrases. But in this work, we're going to sample from the distribution instead, so we get more variety and generate a different paraphrase each time. That sampled path is shown in blue in the tree of paraphrases. And we're going to be using the full distribution over the size of the vocabulary. You can think of the words highlighted in green in the tree of paraphrases as high probability tokens. So here we have the SMART training objective. We're computing the cross entropy loss between the MT model output distribution shown in purple and the output distribution from the paraphraser shown in green. The paraphraser output distribution includes the sampled token in blue, as well as the full distribution over the vocabulary in green. Since we sample each time we train on a sentence, we will take different paths through the tree of paraphrases in order to cover the space of translations. For anyone familiar with word-level knowledge distillation, this is similar, with the paraphraser acting as a modified teacher. One important difference to highlight is that in knowledge distillation, the teacher is typically trained on bitext, but our work only requires that the target language be high enough resource to build a paraphraser, and paraphrasers are rapidly becoming stronger and available for more languages. So just to drive this home, we replaced the one hot reference distribution with the full distribution over the size of the vocabulary taken from the paraphraser, and we're sampling to get different paraphrases each time. So let's look at some results. We will be translating into English using an English paraphraser trained on Parabank 2, which is a synthetic paraphrase dataset. Here I'll be presenting results translating from 10 languages with data from Global Voices. We will be using the SMART objective with 50% probability and standard NLL otherwise. So we do train on the original reference half the time. For more experimental details, please see the paper. So here, I'd like to note that we're looking at very low resource settings. All of our corpora have less than 50,000 lines of training data. And here we have our baseline results. And there we have our method. And we see solid improvements across the board, ranging from 1.2 to 7 blue, with particularly large improvements in low resource settings. If you're interested to learn more, please check out the paper for additional analyses. But there's a couple things I'd like to highlight here. One is that we do compare to back translation, and you can combine the two for improved performance. But one difference with back translation is while back translation is a super common method throughout machine translation, it does require that the language pair be high enough resource to build a reverse direction model. And this can fail in extremely low resource settings. But our work simply requires that the target language is high enough resource for a strong paraphraser. And paraphrasers are rapidly becoming better and working well for more and more languages. And I'd also like to note that we tried the simple approach of just generating full sequences from the paraphraser and training on those. That does work, but SMART works better. If you're interested in other similar lines of work, two of the authors on this paper, Brian Thompson and Matt Post, have a new multilingual paraphraser called Prism that works for 39 languages and is a great MT metric, and that'll be presented at EMNLP. Jao Sadak and I have a paper in EMNLP findings where we apply SMART and Prism to chatbots and analyze their effect on response diversity. And finally, the work I talked about today will also be presented at EMNLP. So to wrap up, we introduced SMART, which incorporates a paraphraser in the loss of a neural machine translation model to simulate training on the full space of possible translations. We demonstrate it is effective in low resource settings, and we release everything you need to try it out yourself. Please reach out if you have any questions, and I'm on the job market this year, so please reach out if you're hiring.